Okay, now Touchstone, our benchmark that was accepted to NeurIPS this year. Touchstone also has a strong focus on out-of-distribution generalization. So we begin talking about what we find is wrong in the standard way people evaluate medical segmentation models. We have 5 main points. The first one is IID testing or in-domain testing. Normally, works are tested with data sets that are randomly split from training and testing. So again, you cannot check for bias, and you cannot check how well this network will perform in unseen hospitals. So medical images can have many changes. So you can have changes in the patient's age, patient race distribution, patient diseases, diagnosis, and you can also have changes in scanner. You can have multiple shifts between hospitals and medical images and CT scans. And usually medical segmentation models are tested IID, so you do not check if the network is resistant to these changes. The second problem in most segmentation benchmarks is small test datasets. So if two networks have similar performance, but they are tested only on 50 images, how sure are you if one is better than the other or not? And if you test them on 10,000 images, if they have the same accuracy difference, should you be more sure that one is better than the other? Yes, because you get more statistical power. So you can create with big test data sets rankings that are much more meaningful, that find smaller differences between similar architectures, and you can really show a trustworthy result that's not due to randomness. And third problem is focus on average dice score. So what do we mean by focus on average dice scores? Many benchmarks rank networks according to average dice scores over all classes, and this hides many of the capabilities of these networks. So is one network better at segmenting the aorta or other tubular structures, and the other network is just better at segmenting a structure like the liver? We need to check with putting more emphasis on these per class evaluations. And also, average dice does not tell you how well networks are resistant to biases. So does one network, is one network more fair in having a similar accuracy across demographic groups like races and gender or diagnosis? So again, average dice score is not a good metric to evaluate that. You need to evaluate our group. And for the fourth point is unfair comparisons. Here, we are mostly talking about the standard benchmarks that we see in most papers. When people propose a new methodology or a new architecture, they will compare this architecture against the states of the art, and normally the same person will train all the architectures. So this is not really fair, because we have more incentive to putting more effort in our own architecture than on the other ones, because we want to show to the reviewers that our architecture is better. So this can create unfair comparisons. And finally, we have short-term outcome pressure. So many benchmarks are only a single edition, so they do not give time for new methodologies to evolve. For example, you can say transformers, when they were just proposed, could possibly not beat CNNs in this test. Or member right now, can it beat CNNs in the future? We need time to discover. So we say that benchmarks should be recurring and not put this short-term outcome pressure to invite more innovation. So Touchstone benchmark or paper is an organ segmentation benchmark, a large-scale organ segmentation benchmark. And we propose these ideals for AI evaluation in medical segmentation, that is evaluation on out of distribution test datasets that can be unseen hospitals or other domain shifts, evaluation on large test datasets, analysis by age, sex, race, diagnosis, and more metadata information to understand biases and fairness of TPR networks, and inviting the creators of the AI models to train their own models, so we avoid the problem of unfair comparisons, and long-term commitment. So doing these periodical benchmarks to allow new methodologies to grow. Here we also propose to invite people, target people that we find have novel methodologies that are significantly different from other methods to participate and give them time to evolve. So here we have a summary of our main contributions. So we invited and had the participation of 14 research teams all over the world. These teams come from 29 institutions in 8 different countries. That's why you have this large outer list here. And also we have the largest scale training and testing sets for abdominal CT segmentation. We have more than 5,000 training CT scans annotated, fully annotated per voxel for 9 classes, 9 organs. We have 6,000 external CTs for testing, and we have 76 hospitals in our training data sets. So why do we need so much scale for our training data sets? Studies show that training data sets that are really large and really diverse increase out of distribution performance. So a big example of this is CLIP, for example. And here we have much more fully annotated CT scans than any other benchmark in these fields. Also, this data set is much more diverse than the other benchmarks in these fields, with 76 hospitals. And also we train with more countries than the other benchmarks. For improving the statistical power of our results, we have by far the largest test data set with 6,000 samples against at most 800 samples here in FLAIR 22. And all of these samples are out of distribution. 5,000 of them are from the JHU dataset, so they are from a dataset never seen during a hospital, never seen during training, and 400 of them are from Total Segmentator. This is about half of Total Segmentator, a little bit less, and it's not an unseen hospital because the other parts of Total Segmentator is in our training datasets. However, we prove there is a big distribution shift between this Total Segmentator set we use it for testing and the one in training. To show that, we show that these two distributions have very different region of interest. So the training images, all of them have 99% of them have all the 9 abdominal organs we are segmenting. So they are really well chosen and focusing on the abdomen, while at least more than 50% of the test images have missing at least one of these organs. So this shows they are not really focusing on the same area. And here we are evaluating another type of distribution shift, that is this region of interest shift. So we also do a multifaceted evaluation. We evaluate models based on metadata, so grouping by sex, age, race, also by diagnosis. And finally, we have our targeted invitation of creators to improve the diversity of the models in our benchmark. So we checked the paper and divided these 14 research teams and others. And we have a really diverse set of models in this benchmark. So we have transformers, we have convolutional neural networks, we have hybrid architectures, we have architectures that use stable diffusion to do segmentation. We have graph-based neural networks. We have multiple frameworks. We have networks based on the NMNet framework. We have networks based on the Monai framework and networks with their own framework. We have vision language models. So by inviting those different models, we could create this diverse set of models instead of just having the state-of-the-art, very similar architectures in the benchmark. Okay, so now finally to the results. Here is our ranking for the JHU datasets, and this table is our results for the JHU datasets. That's our main test datasets. So again, 5,000 CT scans from a hospital never seen during training. Our best performer is MedNext, a neural network based on the ConvNext architecture. Then we have S2Net, Metformer, a transformer. So we have here the first transformer as top 3 with a really similar performance to the top one. And then we have our results also on the total segmentator dataset. And an interesting thing to see here is that we have a big gap in accuracies in DICE scores between these two datasets. So this gap normally goes from 5 to 15 in DICE, but it can get about to 40%. So here you have the results side by side so you can compare. The biggest difference you see is for the SEM adapter. For example, in spleen, in JH8, it gets 88 DICE. And for spleen in total segmentator, it gets 48 DICE. But if you take any other model by chance, for example, the UNICEF in gallbladder, we have 84 here, and here we have 74. So we see a 10% DICE difference across these two OD datasets. And interestingly, the total segmentator results are usually lower. So it shows the distribution shift to total segmentator, even though it's a single hospital, is more difficult to the neural networks than working on a totally unseen hospital. Now to the biases analysis. We, as I said, grouped our test sets JH8 here by metadata, and we compared the network's accuracy according to these metadata groups. And we did a statistical test to see if there were significant difference across these groups or not. So basically we found, yes, normally they are for all of these groups. Those are the results for the average neural network. So this is the average results for all models in our benchmark. And we see a significant difference in DICE score for organ segmentation in race. So for example, white person have significantly higher DICE than African Americans. For sex, again, we see a bias with male being higher than female. For cancer diagnosis, but this is expected, we also see a shift. So healthy patients have more DICE than cancer patients. But here it's expected because cancer can change the organ shapes and the form of the organ, so we expect it to reduce accuracy. And a really interesting result we see here for age. So we observe that from 50 years old, we see a steady drop in average DICE for each age group after that. And all of these drops are significant in relation to the last one. And yeah, this combines with other studies that show that age can make the borders of the organs in CT scans harder to understand. And yeah, this drop is pretty clear in this study. Now we talk about why it's important to have a big test set. Here we have our ranking for the JH8 dataset. So let me explain first what is this plot. Here we have the ranking. So first place, second place, third place, fourth place, and so on. And here we have the models. So this model here is considered the best one, is the first place. And it's the second one, and so on. So to create these plots, we take the test sets and we randomly get subsamples of these test sets. We test the models on these random subsets, and then we check if in these different subsets, if the models maintain the ranking or if the ranking change. So if we have just one ball, it means that this model, for example, is the second place in all of these subsets. Here you have three, so it means that this model has three different rankings according to which one of these random subsets you get. And the larger balls indicate that normally it is in this position. So in JH8, we see a pretty stable ranking. So the first and second place are always the first and second place. Then you have some change from the third to the fifth place, but two of these neural networks are actually the same architecture, just different in size. And then you have a really stable ranking across the entire spectrum. However, JH8 has 5,000 samples. When you go to the total segmentator dataset, as test set with 400 samples here, you see a different story. You see that models change in ranking much more when you take these random subsets of the test sets. So this shows that this ranking is much less stable than this ranking. In other words, this ranking is much more trustable than this. And then you go to the total segmentator official test set that here has about 50 samples, and you see much more changes in ranking when you get subsamples of it. So smaller test sets, less trustable rankings for the models. And here we even consider that this total segmentator test set would be considered pretty large with 400 samples. Still, we get a big advantage by using 5,000. So our conclusions is first, OD evaluation is pretty important, and AI performance can even vary significantly much across different OD datasets. So ideally, we want to test on multiple OD datasets to ensure that medical AI can perform well across the world and across many hospitals. Also, large datasets matter. They make more meaningful rankings. They allow us to find more fine differences across different models. Analysis per organ is very important because it shows strengths of different models that are not shown by the absolute average ranking. For example, a model based on diffusion, a stable diffusion, was the best in some classes, but it was never the best in average ranking. So if we only focus on average, we do not get these nuances. Per group analysis is very important because it shows biases that are hidden by the AI. And we also do per group analysis for each one of these algorithms separately. I do not show here because it's pretty big plots, but it's interesting because we show that different architectures can have different biases. And normally the most powerful, the best performing architectures have less biases than the worst performing ones. Finally, by inviting creators and evaluating all these models ourselves, so none of the creators had any access to these test datasets, we create a fair comparison and a fair benchmark that can be a reference point for future algorithms. So now we go to the last part, that is Abdomen Atlas 3.0, the paper just submitted. What is Abdomen Atlas 3.0? It is an improvement over our Abdomen Atlas dataset, so the training dataset we showed for the benchmark. It has per voxel annotations for organs, for tumors, for blood vessels. It has also radiology reports for all of these CT scans. So we have 9,000 CT scans with paired reports. These reports were created by a methodology developed by us called RedGPT that translates all the information, all the important information in the segmentation into text. So, for example, we will talk about the tumor size. We'll talk about the tumor location. So, which subsegments of the organ the tumor is located. This is very important for planning surgery, for tracking lesions across time. We talk about the enhancements of the tumor in relation to the organ. So hyperattenuation, hypoattenuation is important to understand and classify the tumor. We do staging. So we check the pancreatic tumor relation to the blood vessels around the pancreas to understand if can be removed or not by surgery. For example, if it is encompassing important blood vessel, the tumor cannot be removed because you cannot cut the blood vessel. And we create reports that are really complete. So for radiologists, it's difficult to measure multiple lesions, for example, in a patient. But using this methodology, we can create reports that measure the staging and evaluate all of these lesions.
You are talking about staging,
Yes.
and next slide, I was wondering how many stages you have.
Here I do not have the exact number. Oh, you mean the number of CTs or the number of stages?
The number of stages you try to categorize for.
Four stages, T1 to T4.
Okay. Also,
It's local stage only.
okay, is that you have those information for the report?
No, we are creating the report. So we have this information from segmentation. We have the segmentation of the tumor and the segmentation of the blood vessels. So we can measure the tumor. This is important for staging, and also check if it touches the blood vessel and the angle between the tumor and the blood vessel.
So it's kind of the staging information is created by yourself,
yes,
instead of identified by the radiologist.
Yes,
okay,
yes.
Cool.
Then we ask radiologists to check it, but it's created automatically.
Yeah, yeah. So it's kind of pseudo tumor staging.
Initially, yes, but with the radiologist check, then it becomes not so. So it's like the segmentation. You can create the segmentation and then ask the radiologist to refine and improve it. Also for the report, the same idea.
Yeah, okay.
We use AI to create the report, then we ask, is this correct?
Yes, sounds good. And so your augmented algorithm is applied for kind of many type of tumors?
It's just for pancreatic tumor,
Okay.
because we only have these good segmentations of blood vessels around the pancreas.
Oh, I see.
Yes. But yeah, ideally want to also do it for the future.
Okay, great.
Okay, so we have stage information. We have a total of about 8,000 tumor instances in this data set, and we have 5,000 tumors smaller than 20 millimeters. We have annotations of the pancreas subsegment. So this is the first data set, public data set with pancreas subsegments annotation. So head, body, and tail, and this is very important for staging, because staging in the head is different from staging the tail, and also for tracking the tumor. Also, we have the 8 liver subsegments. That's the largest data set with this information. Yeah, that's basically Abdomen Atlas 3.0. So about future directions, we want to establish collaborations with other institutions like UCSF to continue doing OD evaluation and to expand our possibility of OD evaluation across different hospitals for our models and also for the for benchmarks. We will keep increasing the size and diversity of our data set because, again, it's very important to have large and diverse data sets for high OD accuracy. And a final thing is that segmentation is like a strong type of supervision. We are doing classification per voxel, let's say. So usually segmentation models are less biased than classification models. But then when you go to report generation, so training an end-to-end model to generate reports, that's different from what we did here, that we went from segmentation to reports. If you go from the CT to reports end-to-end, then you are again in an area that's similar to classification. You have labels that are per image and not per voxel. And again, you see, I hypothesize a large tendency for biases and for weak OD accuracy. So another important step is how can we make these models more reliable, OD, more robust, avoid bias, and increase their explainability with new architectures or training methodologies. So that's it.